Hey, we're going to debrief the first page of the free throw shooting activity. So I actually want to begin with question number 5. Okay, so this graph that we made, or the graph that the applet made. Let's see here if I can pull up the one that I did. Oh, well, it decided it wanted to reset. But anyways, I took a screenshot of it. All right. So here were the results of the 100 free throws that I simulated. Okay. So she made the first one, and she was at 100%. Then missed the second one, that dropped her percentage down to 50. Made the next two, so that brought her percentage back up to like 75. And then she missed, and that brought her percentage back down. So if we like connected the dots, we would see she started really well, and then she dropped down, and then she went back up, and then dropped down, up, right? So there's like all these peaks and valleys. Okay. And so let's write down this observation. Okay. So I want you to notice that kind of here at the beginning of the simulation, things have a lot of variability, right? There's peaks and there's valleys. It gets as high as 100%, it gets as low as 50%, and we see things all in between. Okay. So trying to estimate the percent that she makes, it's really hard to do because it's just unpredictable in the short run. Okay. However, we see that when she's taken 80, 90, 100 shots, right, that things are kind of stabilizing now. Like the percent of shots that she's made is kind of settling down here at about 80%, right? So once she's taken about 50 shots, right, we're not seeing a whole lot of change in her percent made. It's just kind of hovering around 80%. Okay, so eventually it settles down to this 80%. Okay, and so let's label that part of the graph here as, the percent made is becoming more predictable. Which is because now we're looking at what's happening in the long run. Okay, so we want to kind of differentiate, right, the fact that early on, percent made is unpredictable. Later on, much later on, it becomes predictable. Okay, this idea of it eventually settling down is called the law of large numbers. Okay, so the more times we simulate something, the better, the closer the estimate gets to the truth. Okay. All right, let's look at question number 7. Okay, so did she make exactly 80 free throws? Well, in my 100 trials, she made 81, so she did kind of slightly better than we expected. Your group might have gotten 80, might have gotten something less than 80 or greater than 80. It really just depends, right? And the idea here is we want to think of these 100 shots as a sample, right? And that sample is only going to estimate the truth. It's not always going to match the truth. Okay. So every sample is going to look different from another sample, and this is called sampling variability. Okay. Different samples are going to look different and produce slightly different estimates. All right, let's look if we ever had a streak of 10. So in my simulation, I had a streak of 10 right there and another streak of 10 right there. So it actually happened for me twice. Okay. Now, is it common? Okay, well, at this point, we don't really know. We can go around the room and poll and see how many groups had a streak of 10, right? If you just want to raise your hand right now, if your group had a streak of 10 in your simulation, right? And the more hands that are up, the more likely that is. The fewer hands that are up, the less likely it is. Yeah. All right. If you want to know, it should happen about 93% of the time, okay, which is kind of surprising. Right. So if we had 100 groups do this simulation, about 93 groups would have gotten a streak of 10, and probably 7 groups would have not gotten that streak. Okay. So it's going to happen a lot more often than it doesn't happen. Okay. All right, the last question, which really kind of brings this activity together. What does probability mean? Okay. So probability describes what happens in the long run. Okay, it's the percentage of favorable outcomes in the long run. Okay, the statistical definition, we call it the long run relative frequency. Okay, and remember, relative frequency is just a fancy word for percent. Okay, so it's the long run percent. Okay, so when we say Mrs. Gallus is an 80% free throw shooter, we don't mean that, you know, if she takes 20 shots, she'll be at 80%, because she almost certainly won't be. And even in 100 shots, right, she won't be exactly at 80%, right? She'll be close. Okay. So what we mean to say is, in the long run, over hundreds, thousands, millions of shots, the percent that she'll make over that long run, right, over all that time, will be about 80%. Okay. All right, so here's a pretty good sentence that describes it in context. So when Mrs. Gallus takes many free throws, so using the word many communicates that we're talking about the long run and not the short run, she makes about 80%. Right? We never say that she's going to make exactly 80%, because we don't know if that's ever going to happen, right? Here, like, we got pretty close, but it's still kind of hovering around 80%. It's not consistently staying at 80%. All right, turn over to the back side. I'll give you the quick notes here. All right, so in the first section, we're just going to define probability. Okay, so the definition is right here. Okay, it's the long run relative frequency. Okay, now we measure probability using numbers, where 0 describes something that never happens, even in the long run, and 1 represents an event that always happens in the long run. Okay. All right, now what's the difference between short run and long run? Okay, in the short run, the pattern is just too unpredictable. Okay, so we can't really estimate what the probability is in the short run, but in the long run, it becomes much more stable. Okay, it's more predictable. Okay, which allows us to then make an estimate. All right, the law of large numbers. So anytime you hear that phrase, think about what's going on in this graph. Okay, again, can't really tell what's going to happen in the short run, but in the long run, the estimated probability approaches the true value. Okay. All right, so the estimated probability of an outcome tends to get closer to the true probability as the number of trials increases. Okay. So our little dot graph here, right? When we only do a few things, right, we're not really close, right? Not really close to 80%. Okay, but the more times we simulate it, right, the more trials we do, the closer those dots are, those estimated probabilities are, to the true value, 80%. Okay. Now, I'm going to suggest at this point that we do the check your understanding as homework, because you guys have a second activity that you're going to do in groups, and this one's going to take more time because you're going to do some simulations and make a poster.